Welcome to IB Chemistry Preparation Exam Tips for both standard level and higher level. Today, through our lesson, I'm going to discuss and to explain Topic 11.1 Uncertainties and Errors in Measurements and Results. Through our lesson, I'm going to teach you how to calculate the absolute, the total percentage uncertainties for all the data taken from the lab. We're going also through the definition of significant figures number. We're going to learn how to find the significant figures number and how to apply on significant figures and decimal places calculations whenever we have addition, subtraction, multiplication, or even division. So let's get started together. The first thing we're going through, it is so important to learn the types of data presented inside any scientific stream. The data is classified into two main types inside the lab. We have firstly the qualitative data. We have secondly the quantitative data. Whenever talking about quality, so we are talking about non-numerical information which are obtained from your observations through applying your lab. So we usually, whenever we want to go through the lab, we can go through qualitative observations. So we use descriptive words. So whenever you want to apply on any lab, you need to look for if there is any bubbles formation, if the chemical reaction was exothermic or endothermic. So you need to follow the change in temperature. You can go through also the texture of the solution. You can refer also to the smell, the color change, etc. All these data, they are qualitative. So they are essentially based on your observations. The second type of data is described as being the quantitative data. Quantity, so we have numerical data obtained from your measurements. So if you start writing, recording the mass, the temperature, the volume, the concentration, the length of something, or even time, so whenever you are going through numbers, you are starting with the second type of data, which is the quantitative data. Here I have a small activity only to make sure that you can know the difference and distinguish between quality and quantitative data. So if you look at this small painting below, and you can start thinking what quality and what quantity data can be taken. So after looking at the paint as a qualitative data, you can start telling me about the colors of the flowers that you have. You can tell me that this painting is made up of oil. You can consider having a beaker or a glass into which water is presented inside. So this is based on quality or observation. But continuing with your quantitative data, you will start maybe counting the number of flowers as red, as yellow, as also the white color. You can maybe go through measuring the total volume of water which is presented inside the vessel or inside the beaker. So after knowing the difference between quality and quantity, now we're going through the assessment of experimental errors. It is so important to remember that all the experiments are never completely reliable. Due to what? Of course, since the experiment consists of errors and we have what's called by the uncertainty inside the measurement data. In the following slides, we will discuss the different kinds of errors and show how a series of measurements can give us an estimate of the precision of any measurement. The first thing we need to learn together now is what is the difference between the word of accuracy and also the word of the precision. Inside your external, they may ask you to write the definition. So yes, both definitions are important. Starting with accuracy, it is how close a measurement is to a true value or to an actual value. For example, if you are inside the lab going to measure the boiling point of something, so you have an actual value to compare with. When you are comparing your data to an actual value taken from the literature, which is a true value, definitely you are going through the accuracy. You can do the same if you are doing an experiment in order to obtain a constant, as Avogadro's constant, for example. So if you've got your experimental measurement value, you can compare it with the actual, which is taken from the literature. Now, continuing with the precision, it's how close the trial's measurements are to each other, which is also considered as the reproducibility of your data. Usually, we quote the precision using the plus-minus value, which is called by the absolute value. Through our slides and our lesson, we will dig deeper into the plus-minus and the absolute uncertainty taken from different equipment and tools. Let's consider another time the precision definition. It's how close the trial's measurements. You need to remember that inside the lab, we usually do more than one trial. So we can perform the trial at least for 3 times. The experiment can be repeated for 3 times or for 5 or even to a higher number of trials. So when you compare the trial's data to each other, you are going through the term of precision. You are not comparing it with the actual value. You are comparing your data one trial to another whenever you want to talk about the precision. Considering here the plus-minus uncertainty, which is given for a piece of wood using the balance, it was measured using the balance. I will talk more about this plus-minus, which is the absolute uncertainty for different tools and equipment later through our lesson. In order to understand more the difference between accuracy and precision, I have here a simple example. A student decided to measure the boiling point of water with a mercury thermometer on different days. So the mission is to find out the boiling point of water. I'm going now to ask you a question. What is the actual value for the boiling point? Of course, you're going to tell me that it is 100 degrees since I'm talking about pure water. So I have here an actual value for the boiling point, which I'm going to use it later in order to compare my data with. She recorded the results in degrees, discuss the accuracy and the precision of the data. So I have here 3 trials taken in day 1 and another 3 trials taken in day 2. So the first thing, what I'm going to do in order to start talking about my accuracy. If I want to discuss the accuracy for day 1, so it is so important to calculate the average value for all trials. Then I'm going to compare it with the actual. So let's start with the average. So for the average value, I'm going to take trial 1. So the first step is to find down the average value. I'm going to put the numbers. So I have 98.2 plus 100 or 1.2 plus I have 99.7, all is divided over 3. And my average value for day 1, it is 99.7 degrees. I'm going now to do the same, but in this case for day number 2. So this is for day 1. For the average value, considering day 2 now, I'm going to write down the final answer after adding 98.7, 98.6, and 98.4 and dividing over 3, your final answer is 98.6 degrees. This is for day number 2. Now I've got my average. I need to compare my average to the actual, which is the literature. So which one, in your opinion, is considered more accurate? Is it the data taken in day 1 or day 2? If you look at day 1, you're going to find that the average value is closer to my actual, which is 100. So what can I describe now? Day 1, in considering the accuracy, I'm going to write that day 1 is considered as being, yes, that's right, it is accurate. But in day 2, it is still now considered as being inaccurate data. So here you remember, or you need to remember, that if you want to compare the accuracy, so you need to go through your average values, then you're going to compare it with the actual, which is the literature. Now let's consider the second, which is the precision part. Look at day number 1 and compare the trials to each other. Trial number 1, it is 98.2. Trial number 2, it is 101.2, 99.7. You're going to find that the data here, it is actually scattered. They are not so close. So I'm going to describe day 1 measurement data as being imprecise. So it's not as precise compared with day number 2. In day number 2, you're going to find that the difference is in decimal, 98.7, 98.6, 98.4. So the values are so close. So I'm going to say that the values here are precise. Now I'm going to go through this diagram. Through this diagram, you're going to find the difference between the accuracy and between the precision. So if you look at the first model, you're going to find that all the crosses, they are far away from my center, which is my target, which is my actual value needed. So I'm going to describe diagram number 1 as being not precise and not accurate. All crosses, they are also further apart from each other. They are far apart. They are scattered away. Continuing with the second diagram, you're going to find that the crosses, they are in somehow closer. So I'm going to consider it as being precise. But another time they are not accurate. If I want to take their average, they are not in the center. Continuing with diagram number 3, you're going to find that they are not precise. Definitely the crosses, they are far away from each other. But if you want to take the average, you're going to find that it is in the middle as an average number. So they are accurate. And for the last, which is number 4, they are actually precise and accurate compared with others. Make sure that you are familiar with these models. They can be a multiple choice inside your external. Now we're going to learn the term of scientific notation. What is the scientific notation? Scientific notation is the way that scientists use to easily handle very large numbers or very small numbers. Of course, we need the scientific notation through our calculations in chemistry, since we deal with large numbers whenever we want to go through Avogadro's constant, for example. So, considering the scientific notation, this is what a scientific notation looks like. A scientific notation, I'm going to find that the C, it's any number which is from 1 to 10, but it's not including the 10. So it could be 1, 2, 3, 4, 5, 6, 7, 8, and 9. After that, it is multiplied by a 10 of a base, and above we have here an integer. So if you look at the examples which are given at the bottom, you're going to find that all these numbers, they are written in a scientific notation way. So you're going to find that you have here a number which is from 1 to 9. Then there is a decimal, and it is multiplied by a power, and you have here an integer number. Could be a positive or could be a negative. Why it's important to go through the scientific notation way of writing? Inside the past papers, and whenever we want to apply on paper number 1, through the calculations, all numbers, they are given in a correct scientific notation. So if you do your calculations, you need to be familiar how to rewrite the number in a scientific notation way. So here, expressing different numbers in scientific notation. For example, number 1, you're going to find that I have here the decimal. So if you want to start taking the decimal and to rewrite the number another time into a scientific notation, you're going to stop right here. So the final answer would be 4.3250452 times 10 to the power of 6 as an exponent. Now I have the second situation, which is having the decimal and start moving to the right instead of the left. So the decimal is right here, starting counting how many places I'm going to take my decimal into. So I'm going to stop besides the 3. So your final answer is 3.61 times 10 to the power of negative 6, and it is to the exponent of negative 6. So you can consider we have two different ways to rewrite the number into scientific notation. You can move either to the left or to the right, and you need to be familiar on either having an exponent as being positive or negative. Now we're going to have a small practice to make sure that you know how to rewrite the number into a correct scientific notation. And from this example, we're going also to learn how to find the significant figures number. So according to the question, express each of the following in scientific notation and calculate the number of significant figures, or find out the significant figures number. So let's start together. In A, what I'm going to do, I'm going now to rewrite the number into scientific. So I'm going to stop beside the 4. So it is 4.37, and it is multiplied by 10 to the power of 4. When writing the number into a correct scientific notation, you're going to find the number of significant figures presented as a significant figures. So the first step is to go through the scientific notation. If you write it into scientific notation, the numbers that appears after writing it into scientific notation, it will be the significant figures number. So here, what is the significant figures number in A? I'm going to write down that your final answer is considered as being 3. In B part, I will start now counting and taking my decimal, and I will stop beside the 4. So my final answer is 4.5 multiplied 10 to the power of negative 7. The significant figures number, according to my final answer, I have only 2 numbers appearing in the scientific notation. In C, another time, I will start counting going to the left side. So this is 4.1754 multiplied 10 to the power of 6, and the significant figures number here, according to the total number appearing, it is 5. In D, I'm going to take my decimal to the right and to stop beside the 4. So my final answer is 4.5, 3 and 2 times 10 to the power of negative 2. Now you can count the total number of significant figures. You're going to find that the significant figures number here is 4. Now for the E, I'm going to take my decimal and start moving to have 3.54 times 10. And the total number of significant figures, it is, in my situation here, is 4. Finally, for the F, it is already given in a correct scientific notation, so I'm not going to do anything. I'm going only to count the significant figures number, and my final answer is 3. We will have now more information about the significant figures number. If you look at this small slide, you're going to find that we have 4 different important zeros. We need to be familiar on the different types of zeros in order to know which one is considered as being counted and which one is not. The first type of zero, it is called by the leading zero. The leading zero, it is actually presented to the left side of your number. You have the in-between zero, which is the zero presented in the middle. We have non-zero digit, which is of course the numbers presented inside your given measurement data. And finally, you have the trailing zero, which is to the right side. So we're going now to learn which one of these zeros is counted and which one is not whenever we want to consider the number of significant figures. Starting with the non-zeros, of course, they are the digits, so they are always counted. As you can see here, I have the number of 3,456. When I'm going to write down the number of significant figures, it's totally 4. I have the zeros which are presented to the left, the leading zeros. These zeros, they are not counted at all, so I will not take them into consideration when counting. So my total significant number here is only 3. I have the trailing zeros, which are to the right side. To the right side, I will always count them. So here I have 3 significant figures, all are counted, but these zeros which are presented to the left side as leading, they are not counted, taking into consideration point number 2. Now I have the zeros which are in between. If we have inside your number, if you've got inside your number a zero in between, of course it is counted. So here I have 4 significant figures. No decimal place. This is a very important point to remember. If the number do not contains any decimal place, all zeros presented, they are not counted inside your number. So definitely here you have only 1 significant figure. To make sure, from point number 5, I'm going now to give several numbers, and we will make sure that we know the zeros presented and which one is considered as being counted and which one is not counted. So let's take these examples. 200, I don't have any decimal, so these zeros are not counted, so here I have only 1 significant figure. Inside my second number, 2020, the zero which is in the middle, it is counted, but this one, since I don't have any decimal, it will not be counted, so all of these are counted only, so this is a 3. In my third example, I have numbers or zeros presented to the left side, they are not counted, but the zero which is to the right, it is counted, so here I have 2 significant figures. We will have now together more activity and examples. So if you look at these examples, I have a number which is considered as counted number, so it is 5 significant figures. In my second, all of them, they are counted, they are normal numbers, so they are 7. Here the zero which is presented to the right side, it will not be counted, so in total it's only 4. And I don't have here any decimal, so all of these, they are not counted, so I have 2 significant figures actually. Let's do this practice together. You may start thinking about how many significant figure numbers should be assumed in each of the following. So for A, since I have a decimal and the zeros, they are in the middle, so all of them are counted, so this is 4. I have a decimal and they are to the right, so they are counted, this is a 3. I have zeros which are in between, all are counted, so this is a 4. The zeros which are presented to the left side from the number, they are not counted, so it's a 2. And continuing with E, the zeros which are in the middle, they are counted, but the zeros which are presented to the left side, they are not, so in total this is 4. Here I don't have a decimal, so this 0 is not counted, so this is a 2. Here I have a decimal, so all zeros are counted which are to the right, so this is a 3. Finally, I have a 2, and here I have a 3 without having any zeros. When you want to count the number of significant figures and you have times 10 to the power of something, you do not take the power into consideration. Now, after learning how to count the number of significant figures, we're going to see why it's important in our syllabus to know and to calculate the number of significant figures. Through our calculations in all chapters, no matter what the chapter that we have, your final answer should be into a correct number of decimal or significant figures according to the rules. So what we're going to start with is so essential and important when applying on calculations. So what we're going to learn now, calculations involving significant figures number. Through our calculations in chemistry, we're going to use either addition and subtraction, and we have multiplication or division. We're going now to start with the first situation whenever you want to add or to subtract. What's the rule? When adding or subtracting, your final answer can only show as many decimal places as the measurement, having the fewest number of decimal places. So you need to make sure of counting the decimal places number. It's not the significant figures. So remember, it's the decimal places. And you need to look for the smallest decimal place presented, and your final answer should be taken. This rule is always taken whenever you have an addition and subtraction. In order to understand this rule more, we're going now to have a practice. Inside this question, I have A, B, C, D, E, and F. So I have an addition or subtraction. I can have my calculator beside me, so you can go through your calculator and you can put the numbers beside each other. So here I have what the calculator says and what's your final answer should be, taking into consideration the rule that we have when addition or subtracting. So let's start. In A part, the calculator says your final answer is 20.69. Your final answer should be how many decimal places? Look at the first number. How many decimal? It's a 2. How many decimal? It's another 2. How many decimal? It is a 1. Your final answer should be only 1 decimal place. So 9 will be rounded to the 6. So your final answer should be 1 decimal, which is 7. Continuing with B. How many decimals do we have in the first number? It's a 2. How many decimal here? It's a 3. How many decimal here? It's a 2. So your final answer should be 2 decimal place, and already the calculator gave me the same answer. Continuing with the C, it's a subtract. How many decimals do we have? It's a 3 right here. How many decimals do we have? It's a 4. So your final answer should be rounded into 3 decimal places. 3 decimal places, so the 8 will give the 3 as rounding. So the final answer is 0.94 as a 3 decimal places. Now continuing with the D, you have an addition and subtract. You will do this as one step inside your calculator. Your final answer, it will be 53.544. Now we will look for the number of decimal places. I have 2 here, I have 1 here, and I have 3. Definitely my smallest decimal place, it is a 1. So my final answer should be only 1 decimal place as given. For E, using the calculator, you're going to find that the answer is 7.82. In this situation, looking at the 7, you're going to find that I don't have any decimal, so no decimal. But for my second number, I have 3 decimal places. So your final answer should be correct into the smallest. So I don't have any decimal and 2 and 3. So it should be only with 0 decimal place. So 8 will give the 7 and your final answer is a 9. The same situation is in F. I don't have here also any decimal, so I don't have decimal places. And you have here 2 decimal places, so your final answer should be without any decimal place. So rounding part, the 7 will give the 11, as if you didn't subtract. So this is in case of addition and subtraction. Now, continuing with the calculations in case of having multiplication and division. In the multiplication and division, we have a rule. The rule says, whenever you want to multiply or to divide, your final answer should show how many significant figures, so it's not the decimal places as addition or subtracting, as the fewest number is presented. So because of that, we started with counting the number of significant figures, and there are a lot of calculations through your IB syllabus. So it is very important to be familiar on counting the number of significant figures. So at the end, whenever you want to do calculations, multiplication and division, take into consideration your smallest significant figures number. Let's apply. I have here I, double I, triple, and 4. So in I have a multiply and to divide. Using your calculator now, this is what the calculator says. Start counting now the number of significant figures, not decimal places. So this is a 3, and this is considered as 4. Make sure that you know how to count the zeros and to know whether they are counted or not. So refer back to the rules that were discussed previously. So this is 4. So your smaller number of significant figures is 3. So you need to rewrite your number into 3 significant figures. So the 8 will give the 0, so it will become a 1. The zeros which are presented to the left, they are not counted. So this is your final answer into correct 3 significant figures. Continuing with double I, you have here 3 significant figures. Here you have only 1, and here you have 2. So your final answer should be only 1 significant figure. 6 will be rounded to the 2, so it will become a 3. And this is correct into 1 significant figures, which is the smallest according to my calculations. I have the third example. I've got here 4 significant figures are given, and here it's a 3. So your final answer should be 3, and these are the 3 significant figures. So my final answer is 3 significant figures. You can rewrite this number into the scientific notation if you want, and you can leave it as it is inside paper 2. For 4, you're going to divide. You have 4 significant figures. You have here 3 significant figures. So your final answer should be 3 significant figures only, taking into consideration the fewest number presented. Now, after learning how to find out the correct number of decimal places or the correct number of significant figures according to the calculations, we need to go into the second part of our lesson today, which is the uncertainty in the numbers. We're going to learn how the numbers are classified as being uncertain, and through our lab, how can we determine the total percentage and what is the meaning of absolute uncertainty as well. So we will start now with the uncertainty in the numbers. We've got 2 types of numbers. The first type, it is the exact number. The second type, it is the inexact number. When talking about the exact numbers, they are the values that are precisely known and not associated with any uncertainty. But the inexact numbers, they are the values that are associated with a degree of an uncertainty. To be more clear, I'm going to give an example which is at the bottom. Here I have 2 masses taken from a balance. I'm going now to label the exact number presented. Using the balance, I'm sure that 65.4, it is an exact. So this is an indication that this mass taken for the piece of wood or anything that we have, it is exact. Where is my inexact number? It is the last decimal reading. So the 3 here, it is my inexact number. So this is inexact. Here comes the uncertainty. So I'm not sure whether this number is correct or not according to the sensitivity of my balance. It could be 3, it could be above as 4, it could be below as being 2. But the 65.4, it is considered the exact number. So I'm sure that this number is a correct number. And if I've got an error or uncertainty while measuring the mass of the piece of wood, it will be in the 3, which is the last decimal inside your number. So we can consider the inexact number as the last decimal place reading. Place reading. We have now another example as another value for also a mass, which is a 23.256. You can find that the exact numbers are 23.25. All of them are considered as being exact. I'm sure that these numbers, they are exact. But the last decimal reading, which is the number 6, it is the inexact number reading. The uncertainty comes from this inexact number reading. So we have here a simple example. If I want to estimate the length of a pencil using a ruler, and according to my small diagram here, you can find that the length, it is between the 6 and between the 6.5. So if different students started to read the number, so here we have more than one value estimated. So maybe I can read it as 6.35 in the middle exactly, or I can read it as 6.36 or even 6.37, or perhaps another student may tell me that this is 6.34. So in each time the last decimal is considered the uncertainty reading, which is the inexact number presented. So two numbers, they are certain, they are exact, and one number is considered as being inexact right here. Continuing with recording the uncertainty value. Whenever we want to record measurement inside our lab report or inside any experimental data, all numbers, they are given in this form, into which we're going to write down the value, and beside the value we're going to write the uncertainty, which is plus minus, taken from the equipment or the tool used beside the unit. For example, if I use a graduated cylinder to measure the volume of water, and the water volume, it was a 25.00, I'm going to put plus minus the uncertainty, which is called by absolute, and we're going to learn how to find it now. For my graduated cylinder, it is 0.05. Then I'm going to close brackets and to put beside it the unit taken for your volume, which is a cubic centimeter. This is so important whenever recording uncertainty value, and this will help you through writing your lab reports and your internal assessment. When talking about the uncertainty or the absolute, most of the time the uncertainty as a plus minus can be found on the equipment itself. So if you read what is written on the equipment while applying on the lab, you will find that the plus minus as an absolute uncertainty is given. So you can record it directly. Now, if you are going through a digital equipment, the uncertainty is the smallest unit the equipment can measure. How is that? I've got here different equipment and tools used inside the lab. I have two different digital balance. I have also a thermometer, a digital thermometer. If you look at the first balance, you will replace the last decimal, which is the inexact number, by the number of 1. So the uncertainty for this digital is plus minus 0.001. So the uncertainty or the absolute for a digital equipment, it is the replacement of the inexact decimal number by the number of 1. Continuing with the second balance, you're going to find that it is giving me two values or two decimal places. So if you replace the last decimal, which is the place of the inexact number, by the number of 1, so you have the absolute uncertainty of this balance. If you compare the absolute uncertainty for each balance, you're going to find that there is a difference in the number of decimal places. Here there is an important question. We need to answer it together. Which one, in your opinion, is more precise when you want to go to the lab? You have the option to use balance number 1 and you have the option to use balance number 2. Definitely, the values taken from the first balance, they are considered as being more precise. So it's better to use it actually. So the first balance is more precise compared with the second. Compared with the second, so this one is more precise. More precise. And this one is less precise. So inside the lab, if you have the opportunity to use different tools with different absolute uncertainty, you need to look for the one which give you more decimal places, since it will be more precise. For the last example here, you're going to find that the value which is written according to the thermometer reading, it is 61.9 degree. So the plus minus is to replace your last decimal by the number of 1, which is the inexact number. Now we're going to learn how can we find the absolute uncertainty and how can we record the uncertainty if we are using manual or analog equipment instead of the use of a digital equipment. So inside the lab, if you are using a graduated cylinder or using a pipette or using a burette or even a thermometer which is not digital, how can you find the absolute uncertainty? In some situations, the uncertainty, it will be written direct on the equipment used. But if it's not, so you need to find it out in order to be able to continue writing your internal assessment and lab report. So how can we find the uncertainty for an analog equipment? The uncertainty is half the quantity which is between markings. In order to understand what is the meaning of half the quantity, let's look at the figure which is presented here to the right. I have here a graduated cylinder which is used to measure a specific volume of solution. So if I'm going to read the volume, I'm going to find that it is 43 milliliter or cubic centimeter. In order to find out the marking or the least digital, so I'm going now to zoom. What do we have inside the scale? So I have here a 40, and in the middle part I have the 45, and I have here the 50 as a volume. Between the 40 and between the 45, you're going to find that you have smaller possible scale. So if you want to read, you're going to find that you have a 40, you have a 41, you have a 42, you have a 43, etc. So you're going to find that the least digit possible is a 1, which is the difference between one number and another. So the smallest possible digit that you can read using this graduated cylinder is 1 cubic centimeter or 1 milliliter. So the rule when you want to calculate or when you want to record the uncertainty, as an absolute, it is half the least digit. So you're going to take it as half multiplied by 1, and your final answer, it will be plus minus half milliliter or cubic centimeter. It is so important in the absolute uncertainty to make sure to have the plus minus while writing. Now, we're going to go through how can we calculate what's called by the percentage uncertainty for different measurements after applying on your calculations. Actually, this part is so important and so essential for your external. And inside paper 2 and paper 1 as multiple choices, you need to be familiar on calculating the percentage uncertainty. After finishing the whole unit as 11.1, there will be a practice on past papers to look for how the percentage uncertainty comes into multiple choices and inside paper 2 as well. So let's start with what is the meaning of percentage uncertainty. Percentage uncertainty, it's the ratio that compares the size of the absolute uncertainty as plus minus to the size of the measured experimental results. We have here a rule. To calculate the percentage uncertainty, you need to take the delta A. Here I'm talking about the plus minus as absolute for the equipment or the tool that you have, over the value, and you need to multiply by 100%. I've got here a very simple example. If I am measuring the volume using the graduated cylinder, and the volume is a 25 plus minus 0.05 cubic centimeter. So the percentage uncertainty, you're going to take your plus minus value, which is your absolute 0.05, you're going to divide it over 25, and you're going to multiply over 100 to multiply it by the 100%. So your final answer is 0.2. This is called by the percentage uncertainty while applying on your calculations. We're going now to go deeper into how to propagate the uncertainties. When performing calculations with 2 or more values, each with their own uncertainties, the uncertainty of the final value must be calculated. Of course, inside the lab, when you're going to go to the lab, you've got data. You will take the data taken from the equipment and tools, and for each data, there is plus minus uncertainty. You will use the data in order to apply on calculations later. So for example, you will be calculating the mole, you will be calculating the concentration, you will be calculating the density, etc. Your final answer should be given into a correct answer using the significant figures number besides giving the percentage uncertainty and the absolute for your final value. And this is what we're going now to learn. So let's start with the first type of calculations. If you are applying on adding or subtracting, what's the rule? When adding or subtracting, the absolute uncertainty should be added. So let's apply on this simple example. I have here 2 values taken from the thermometer, which is T initial and T final, and you have beside each the plus minus uncertainty, which is taken by the equipment of your thermometer. So as a T initial, I have 34.5 plus minus 0.05 degree, and you have 45.21 plus minus 0.05 degree. You want to calculate the change in temperature. The change in temperature, it will be T final minus T initial. So you're going to subtract 45.21 minus 34.50. Remember that when applying on subtract, your final answer should be a smaller possible number of decimal places as we discussed earlier. So it is 10.71. This is as a degree. Now, for your final answer, you need to tell me what is the plus minus uncertainty for your delta temperature. So the plus minus for your final answer, whenever you are adding or subtracting, is to add both uncertainties together. So what you're going to do, you will add 0.05 plus 0.05 and your final answer is 0.1. This one is your absolute uncertainty for the thermometer and should be given beside your final answer inside your lab reports. So from here, you should keep inside your mind, anytime you are doing addition or subtracting for any two values and you have an uncertainty for each value presented inside your law, so you need to add both values as uncertainties together. You can further calculate the percentage uncertainty for the delta t. So in this situation, since you already know that it is plus minus 0.1, so you will take 0.1 and you're going to divide it over your value, which is 10.71, of course, times 100%. And after that, you will use your calculator and find out your final answer. So you will start firstly with the absolute, then you will continue by the percentage uncertainty. Now, the last thing that we need to learn for today is how can we propagate the uncertainties in case of multiplying and dividing. So if you are applying on multiply or divide, I have rule number 2. When multiplying or dividing, the percentage uncertainties in this situation should be added. So I'm going to add the percentage uncertainties, not the absolute. So let's learn how can we apply on that. I have here an example. Through the example, I have the length of a box. I've got it as 5.3 plus minus 0.2 meter. Its width is 4.8 plus minus 0.5 meter. And its height is 3.6 plus minus 0.4. You want to calculate its volume in meter cube, and you need also to include its percentage and absolute uncertainty for the final volume. So let's start with our answer. The first step is to calculate definitely the volume of this box. So the volume, it will be, you will take your length and you're going to multiply it by the height and you're going to multiply it by its width. So I'm going to apply, it is 5.3 multiplied by 4.8 and multiplied by 3.6. Using, of course, the calculator, your final answer is 91.584 cubic centimeter. Now, let's take into consideration our final answer. How many significant figures my final answer should be? Here, you need to remember that we need to take into consideration how many significant figures is given inside all numbers. So, since you have two significant figures, so here you have a 2, and here you have another 2, and here you have also another 2. So your final answer should be two significant figures. So L5 will give the 1, and your final answer should be written as 92 meter cube. So it's so important as a final answer to take into consideration the number of significant figures as discussed earlier. Now, I've got my volume. I'm done with the volume of the box. Now I need to continue by the percentage uncertainty of this volume. Of the box volume. What I'm going to do, according to the rule, I need to take the percentage uncertainty of each variable presented inside my law. So my percentage uncertainty for the volume is the percentage uncertainty of length plus the percentage uncertainty of width plus you will take the percentage uncertainty of height. So you need to include all the variables as percentages and to combine them together. So now we will apply on each. So we will take for the first one, it is 0.2 divided over 5.3 multiplied times 100%. Now you will add the second, which is, open brackets, you have a half. I'm taking the absolute from the question times 100%. Finally, I have 0.4 divided over 3.6 times 100%. So you need to take the percentages of each variable and to add them together. So the total percentage uncertainty of the volume using the calculator, it will be 25.3%. After calculating the percentage uncertainty, you can continue by the absolute uncertainty. In order to find the absolute uncertainty, which is the plus minus uncertainty for the volume, you will take your percentage, which is a 25.3 over 100. Then you're going to multiply by the volume of box, which is the value that you have obtained previously. So I'm going to take now 25.3 over my 100, and I'm going to multiply by my volume, which was the 92. Using your calculator, of course, you need to have the plus minus, and it is very important to include the plus minus when applying. And if you didn't include it inside your external, if the question is asking you about the absolute uncertainty, so you will not be able to take the answer, which is 23.3 meter cube. So let's go another time to the question and make sure that the steps are clear. So here we are dealing with calculating the volume of a box, taking into consideration how to find out its percentage and absolute uncertainty. So we started firstly with number 1, which is calculating the volume. We took the length, the height, and the width, and we multiplied by each other. Then we take into consideration having your final answer into correct number of significant figures, which is 2. After that, we continued with the percentage uncertainty of the box. So you need to take the percentage uncertainty of each variable presented. So it is the percentage of the length plus the percentage of the width plus percentage of the height. We apply to find out the total percentage of your volume. Finally, you're going to go through the absolute, into which you will take your percentage, you will divide over 100, and you will multiply it by the value. Your absolute should be always plus minus uncertainty. So in 92 meter cube, it is with a plus minus 23.3. You can write it as 23 only. Now we're going to have another example, and this is the last example for the calculations. In example number 2, using a balance, 2.5 plus minus 0.01 gram of KMnO4 was weighed using a balance. Calculate the mole number. So here I'm trying to apply on chemistry. So in order to calculate the mole number, you need to remember that the mole equals the mass, and you're going to divide over the molar mass. The mass is given as 2.50. Then you're going to divide over the molar mass of KMnO4 taken from the periodic table as K and Mn, and you've got 4 times 16 for oxygen. I will write down the final answer. Using the calculator, the mole number, it is 0.0158. The final answer is 3 significant figures, and it is correct since here you have 3 significant figures, and Your molar mass is 4 significant figures, so your final answer should be correct into 3 significant figures. The zeros which are to the left side, they are not counted. Now I'm going to calculate the percentage uncertainty of my mole. So it will be the percentage of mass plus the percentage of the molar mass. Here there is one important note I need to mention. Since the molar mass is considered a constant number, the molar mass is without any uncertainty. We take it from the periodic table, so it will not be included as a percentage. So the percentage uncertainty of the mole here, it will be the percentage uncertainty of the mass only, without taking the molar mass. Remember that you will take all the variables presented inside your law, and if there is anything constant as being molar mass, for example, or if you apply on Avogadro's constant, or if you've got PV equals nRT for the R, for example, it is considered as being constant as well. Any constant, there is no percentage. So now I'm going to apply on the percentage of the mass, which is 0.01, and I'm going to divide over 2.5 multiplied times 100%. Using, of course, your calculator, it will be a 0.4%. So this is my percentage uncertainty of the mole. Continuing with the absolute uncertainty, I'm going to take my percentage, which is 0.4, divide over 100, and I'm going to multiply it by my mole number. And definitely I need to add the plus minus. Using the calculator, it is 6.32 times 10 to the power of -5 mole. This is my last example for our lesson today on how to calculate the percentage and the absolute uncertainty in case of having addition, subtracting, or even multiplication and division. In my second lesson, I'm going to continue in chapter 11.1. I'm going to give you the types of errors. Then at the end, we're going to have practice on past paper questions based on chapter 11.1 taken from chapter paper 1 and paper 2 as well. Thank you for watching.